Okie dokie. Good morning, everybody. It's great to have you all here, wherever you may be. Thank you for joining this webinar. It's currently a temperate winter morning in Johannesburg, and I welcome you all to my webinar today, where I'm going to tell you all about how I taught a machine to see. And this is going to be a story about anomaly detection in industry. Some housekeeping rules before we get going. Please ensure that your microphones are on mute during the webinar, and it will be recorded, today's session, and posted on social media at a later point. If you've got any comments or questions, I welcome them, but please could you pop them into the chat box and we'll address them at the end during Q&A. Some background about me. My name is Verushen Coopoo, and I'm a specialist in data science and modeling here at Opti-Num Solutions. My academic background is in biomedical and electrical engineering, and by all means, please feel free to get in touch with me. You can scan the QR code over here on the right to get to my LinkedIn profile, and this one here on the left will pop me an email from you. I'll give you a second or so if you'd like to take a screenshot of these QR codes. Moving on. A quick introduction to Opti-Num Solutions and who we are. We are a management consultancy company who partner with our clients in order to develop data-driven solutions to complex business problems. We are the sole resellers and distributors of MathWorks of the Southern African region, and you may be familiar with some of our clients, names like MTN, Nedbank, Anglo American, and these clients and the work we do really spans many industries, from business analytics to finance, mining and manufacturing, digital engineering, and the research, teaching and learning or education space. Without further ado, let's jump in to what we'll actually be covering today. And I'm going to give you some context and tell you a bit about what anomaly detection is. We're going to go into a case study of some anomaly detection work that me and my colleagues have done. And we're going to do a demo on something called FCDD. And that will be done in MATLAB. And some more information and lights will be shone on that in due course. Then we'll wrap things up. What is anomaly detection? And this is quite an important concept for today's webinar. It's first important to define what an anomaly is. And this is any sort of data or suspicious event which stands out or deviates from a normal pattern. And this could be any type of data. It could be images or signals, but in this presentation, we'll focus on images. To give you one sort of idea of how an anomaly could be represented, in a tangible sense, most of us are familiar with outliers. Say we have this time series here, as shown in blue, a point which is very different from the rest of them, this red one up here, could then be classified as an anomaly. Now, I can say this, you can say this by using our human reasoning and looking at the graph, and there are levels to this. There are mathematical models and equations you can use to verify or to label this point as an anomaly. There are machine learning and deep learning models you could use to do the same thing. And in this webinar, I'm going to take you through how I actually use machine learning in order to achieve this. There are several different types of, or rather several different applications of anomaly detection. One of them is in medical diagnostics, and this applies to disease detection. Anomaly detectors can be used in medical images to do things like detect cancer, lung disease. Like you can see here in this image, a red bounding box has been drawn around this lung because it's been collapsed. You can also use it in many other medical fields like neurodegenerative diseases, amongst others. Next up, Anomaly detection can be applied in cyber attacks or to detect cyber attacks. And these include things along the lines of cybersecurity, computer networks, national surveillance. For example, if some anomalous traffic patterns are detected within a certain network, this could be a sign of sensitive data leakage from a hacked computer. And of course, this is a terrible scenario and should be avoided and tried to be dealt with as quickly as possible. Anomaly detection can also be used to detect fraud, and this could be in many sectors like insurance or banking. You can look for different behaviors and patterns in banking apps or even with how customers interact with their own capital. There could be signals which stand out here, which are indicative of anomalies. And lastly, anomaly detection can be applied in the manufacturing space, where over here we're looking for fault or damage detection. You can see here's something that looks a lot like a gear, and at this point, the edge is a bit broken, and a red bounding box has been put here, let's say automatically, to try and detect that in order for quality assurance. It's better to have, in most of these cases, an algorithm which can spot these things that maybe a human could miss or that won't get tired. A human will inevitably get tired, and I'm not trying to make a point about any ominous robots uprising, but that is a point or an advantage of using machine learning based anomaly detection approaches for things like this, for tasks which can be repetitive and which can have a similar thread or similar pattern to them. I'm going to move on and describe some MATLAB models that are used for visual anomaly detection. So in other words, using anomaly detection for image data. Now, there are many models which exist, but I'm going to go through 3 of them which exist in MATLAB. The first one, and it's going to be the subject of our demo today, is the FCDD, and that stands for Fully Convolutional Data Description. Now, this is a type of network which takes training images of normal and abnormal images and translates them into something called a latent space. You could think of the latent space as an ultimate dimension, much like the upside down in Stranger Things. Now, when using an FCDD, there are significantly less demogorgons because what it does is compare input images to the representation in the latent space to figure out if those input images are actually anomalous or normal. The next type of model is something called fast flow. And this is a two-dimensional flow model, which has a lightweight structure. That's what makes it fast. And it's used to project the feature distribution of normal images into the standard normal distribution. And these probabilities are used as the anomaly score or the amount of anomaly in testing. It's important to note that when I say normal distribution, I'm talking about the bell curve, your standard Gaussian distribution. And lastly, there's a model we call patchcore. And this model learns an embedding of what normal looks like, such that if anything abnormal comes along, it compares it to its idea of normality, of the norm, and it's able to flag anything that's abnormal. So you can imagine somebody trying to create a mental image, trying to remember what normal looks like. And they're trying to apply this mental image, this memory, every time a new image comes in to be able to check for anomalies. Now, this model is very effective, but it can be quite memory intensive. Of course, the type of model you choose depends very much on many factors, including the data you have available and your application. And these are all things that me and my team can help you discuss in more detail if you have questions around this. I'd like to give some context and information about a case study that we did at Opti-Num, and this was to apply machine vision in medical devices. You can see over here, we have an image of a broken femur, the femur being your thigh bone. And this is what is termed a compound fracture. In other words, it's a clean break. The femur has broken into two pieces and the bones haven't shattered or splintered into many smaller pieces. All right. And this was the subject and the type of data that we used in this project. So our challenge that we faced and that we wanted to solve for our client is that radiologists and trauma surgeons, people who would work with these type of images, are a scarce skill. And full body x-rays in trauma situations need to be looked at quickly because time is of the essence, especially in an emergency situation. But it's complicated by the fact that specialist medical practitioners are quite scarce in South Africa. What we did was use image processing and deep learning techniques in order to detect compound fractures in femurs, much like the one you see here on the right-hand side. What we then did was deploy this functionality into a C++ helper library, which integrated with our client's system or X-ray viewer. And in the end, we developed a feature which can point the radiologist within 99% accuracy of whether a compound fracture, is present in the femur within 20 seconds. Some examples of the results of this case study is you can see here something called a heat map, and I'll be discussing heat maps in a lot more detail quite shortly, where the hot or brighter spots of this heat map actually show you the point of anomaly. So they show you here where the bone was broken. And you can see in a couple of examples of full body images, a yellow bounding box has been drawn over the femurs in which there are a compound break. In 4 months, we were able to demonstrate the complete integration of an AI advisor feature into existing medical device software architecture. So using a small subset of label X-ray images, we solved this machine vision problem by leveraging our experience in data science and engineering. We built a streamlined and collaborative platform from prototyping to production by using our software engineering expertise to deliver quality. Our modeling and integration outcomes were particularly successful due to the close partnership we were able to leverage with clinicians by using the MATLAB image labeler application, as well as the product software team by collaboratively writing shared helper libraries in C++. It was really cool to be part of this project with my colleagues, and I'm showing this as an example of the application of anomaly detection in this field, which we were able to successfully implement and go through. Let's move on to our demo, or a precursor for our demo for today, shall I say, which is the FCDD network. So the FCDD is a type of convolutional neural network which takes an input image. You can see over here, image X is an image of a hazelnut, and this network has been trained to look for defects in that hazelnut, probably most likely for quality assurance purposes. It then passes through the architecture of this neural network, which is convolutional in nature. It consists of many layers, and it develops a representation of the images in something called the latent space. You can see here, it's denoted by phi of omega of X. And what this gives us right at the end is something called a heat map. And the hot parts of this heat map actually correspond, I hope you can see, to the parts of the hazelnut which are defective and which deviate from the norm. I want to give a bit of context on this concept called a heat map. It's called a heat map, but it doesn't have anything to do with physical temperature or degrees Celsius. It's an indication of the strength or the magnitude of the anomaly at each point of the image. However, the word heat map is a lot catchier than indication or magnitude of the strength of an anomaly in an image. So we call it a heat map. And this is really important because I'm teaching this machine to see, but more importantly than that, it also needs to tell us why. What is it seeing and why is that abnormal? And the power of the heat map is that it very clearly shows which parts of the image are actually abnormal. And that's really important because it speaks to something which you may have heard of. It's become quite a big topic of late, and that's AI explainability. Can we actually interrogate and take apart why a network does and says what it is? Our FCDD is going to give us this heat map, which is an indication of the anomaly detection. And it's also going to give us a classification, whether or not this image is normal or abnormal, whether it's an anomaly. Let's discuss this idea of normal versus an anomaly in more detail. The example that we're going to cover today is that of pill quality assurance. I thought that this was quite a nice marriage of a medical and manufacturing example. And we're going to try and figure out whether our pills that we have manufactured are normal or whether they have imperfections. And in this data set, the possible imperfections are they could have dirt on them or they could be chipped. And as I mentioned before, what we're going to see are heat maps. Now, a heat map is just an image, and an image is just a matrix, and a matrix is just a set of numbers. That is a fact which I want you to think about, and I'm going to bring it back very shortly. This is an example of a normal pill with the heat map superimposed on it. And it might not actually be obvious to you that there's a heat map over this until I actually show you an example of an abnormal pill. So what you can very clearly see is that where this pill is chipped, where there are imperfections in it, there are brighter spots on the heat map. And this is indicative of an anomaly. Now, I mentioned to you that a heat map is just a set of numbers. So what's something we can do to a set of numbers? Well, in data science, we love to draw graphs. So here's a histogram of the distribution of the set of numbers which come from this normal heat map. And what I'd like you to observe is that on the x-axis, we have the anomaly score. And this basically corresponds to the amount of anomaly in every single pixel in our normal heat map. And you can see that a lot of them are centered at 0, meaning there's low anomalies or no anomalies rather in those pixels, and it slowly tapers down and increases slightly. Now, I want you to take note of the fact that these numbers are actually very small. The largest number is around 0.06, and the average value in this distribution, indicated by this red dotted line, is around 0.01. I'd like you to compare this with the same distribution of the abnormal heat map. And at a quick glance, these two distributions look quite similar. But if you take note of the values on the x-axis, you'll actually notice that the anomaly score for the abnormal heat map, those numbers are much bigger. And that's really because there's more anomaly in an abnormal image, as you'd expect. These pixels, these bright pixels from the heat map, are actually what contribute to these numbers being a lot larger. And we can see here that the average value in this image is around 4, indicated by this dashed blue line. I want you to try and think where I'm going with this. If we can find out somehow a magic number, I want to call it that, which represents a threshold above which all classified images are abnormal and below which all classified images are normal, then this could actually help us classify each image as normal and abnormal, in addition to having this heat map for explainability. And the next question is, well, what is this threshold? And in order to get that threshold, I'm going to take you through the data and how I've split up the data. Now, in any machine learning or deep learning or modeling approach, you're often going to split up your data set into various groups. And in this case, we have a training, calibration, and testing data set. Now, these numbers are guidelines. There's no hard and fast rule. This is a rule of thumb. There is no regulator who is going to shout at you for choosing these numbers however you'd like to. However, this is my recommendation, and this is from experience what I found has worked. So our training set from our database of images of pills, we're going to take 60% of them and actually use them to train the FCDD, and this is going to learn how to make these heat maps. The calibration dataset, which is 30%, is actually what's going to be used to try and get that threshold of what's normal versus abnormal. And then the remainder, our testing set, needs to actually be used to gauge the performance of our classifier and our heat map. So this evaluation of the performance, it's a really important part of any data science workflow, and it should never be neglected. Of course, this data split 60, 10, 30, it really, like I said, depends on many things, including the data you have and your application. Let's jump into our MATLAB demo. And this is the point at which I'm going to show you how I taught a machine to see. And what's a really important outcome here is we need the machine to tell us this pill is abnormal or this pill is normal, and we need to know why. And that's a really important part of machine learning explainability. I'm now going to move into MATLAB. And let's begin the demo. What you'll see in front of you is my MATLAB version release 2023A. And let's go through this demo, which I have adapted from an existing example. And I will send you, like I have with previously shown some QR codes in this presentation, a QR code taking you to this example, where you can have a look at it for yourself. In this demo, we're going to be looking at how do we take an image and predict whether it's normal or abnormal, but also add a flavor of explainability to it. How do we superimpose a heat map, which actually shows, hey, here's the biggest concentration of dirt, and the rest of this pill is actually quite dirty as well. Of course, as I mentioned, this would be important for quality assurance purposes. All right. The first thing we're going to do is we're actually going to get our data set. And this is an example of the data that we're going to look at. The pill will either be normal with no imperfections, it'll have some dirt on it, or it will be chipped. Let's load and pre-process the data. And this is done using a construct in MATLAB called an image data store. And this is a really useful way of working with many images, possibly even hundreds and thousands, without running out of memory. Of course, in this example, we don't have many images. It's a proof of concept. And as you'll see later on, it's a very idealistic example. And the data that you will likely come across and that I have come across working on real life client projects is not ideal. And there are many ways to work around that. The first thing we're going to do is we're going to split the data into its different sets. So 60% for training, 30% for calibration, and the balance, which is going to be 10% in this case, for testing. And this is a really cool MATLAB function, split anomaly data. And what it actually shows me is per each of the different classes I have, normal, chipped, or dirt, what is the spread of the images in each of those classes per my 3 datasets? Over here, for example, we can see under input, under all the input files, 43 of them have chips in them, and that corresponds to roughly 13% of the input files having chips on them. Over here, you'd often see the word validation used. In this example, it's synonymous with calibration, and we have 41 images of dirty pills, with corresponding to, coincidentally, 41% of the images in the validation set being of dirty pills, and so on. This is a really useful function because it actually shows or gives insight into what your data looks like and what's being used to train your model. And of course, that's quite important for model governance purposes. Next up, we're going to augment our training data. And data augmentation is a really important and valuable step in the model building process. It doesn't only have to apply to images, it could apply to signal data as well. And image data augmentation is a really sneaky way of synthesizing artificial data to make it appear that you have more data than you actually do. Because a general rule of thumb in machine learning is the more data you have to train your model, the better. Now, ways of synthesizing artificial image data include applying rotations, horizontal or vertical flips of the data. You could affect the contrast. You could introduce some noise into the image. All of these techniques actually make as if there are more images than what they actually are. And the point there is that it's going to give you a more robust model. If we look at the augmentations that have been done on the pill dataset, you can see from the shadows and the three-dimensional parts of the pills, they have generally been switched around and they have been rotated. This is just a simple example of image augmentation in order to demonstrate the concept. Like I said, there are many different types of augmentation techniques which exist. Now we're going to create our FCDD model. And this is going to be done using a technique called transfer learning. And with transfer learning, you're actually going to take a network which has been pre-trained on something else, and you're going to modify it slightly in order to suit your application. So the network we're using as a backbone is called Inception v3, and there are many types of pre-trained networks already built into MATLAB that you can use. And this backbone is going to be sent in to our anomaly detector. And we use this function here called FCDD anomaly detector in order to build this network. Now you need to, like I said, transfer learning does the bulk of the work for you. You've got to finish it off. And that's by doing some additional training on the network. On my computer with this data set, which is relatively small, and the images themselves are relatively small, both in terms of size and number, it takes about 20 minutes to train on my computer. In order to save time today, I'm just going to load the image, the network that I've already saved and trained at an earlier time. Now, you might be interested as to what these things are. They are called live controls. And the really useful thing about the live script that we've been using, this document is called a live script. And it might look a bit familiar to you if you're familiar with Python. It's analogous to the Jupyter Notebook, but the live script allows you to intersperse code, text, instructions, outputs, all into one coherent linear document, which you can then export and share. These items are called live controls, and they really allow the live script to become even more alive and more interactive. We can see here that we can change the number of epochs for training. We can actually specify whether the training should be done or whether it should be skipped. In our case, it's going to be skipped. And there are several other live controls like buttons, drop downs, and numeric sliders and spinners. So since the training is set to false, I'm just going to load the network from a pre-existing mat file. You can see here that if we had done the training, these are the hyperparameters we would have chosen, and this would have trained our FCDD anomaly detector. Up next, we're going to choose our threshold for our network, okay? We need the network to decide on a number above which everything will be abnormal and below which everything will be normal. I'm going to run this section of the code, and what it's going to do is it's going to take our calibration data, pass it through our detector we have trained, and actually give out scores. So we had 99 calibration images, and for the first image, its average score was 3.1, the next was 2.7, the next was 3.2, and so on. The labels for those images, we can see that the first couple are 1, being that they are abnormal. They are abnormal images, and so these couple of scores all correspond to abnormal images. Okay, now, similarly to how I had plotted histograms before of a single image per normal and per abnormal, let's actually have a look at a distribution of the mean scores of all the normal images in our calibration set and all the abnormal images in our calibration set. And when we do that, we land up with a histogram below. Now, as I mentioned, this is a wonderful example because everything works out perfectly. And the reason why I say that is because we can see all the normal images have a mean anomaly score, which is quite low. They're all below 1. All the abnormal images have a mean anomaly score, which is much higher. So we can see here that in order to develop a threshold, there's actually quite a clear and neat separation between the normal images and the abnormal ones. In a real-life case, with working with messier data, you might find that these distributions overlap a bit more, or perhaps the distribution is too complex, the data is too complex as it is, in order to create a neat-looking distribution like that. And in that case, some other techniques might have to take over. But to prove the concept today, we can see that there's a nice clean separation between our normal and abnormal images in our calibration set. Let's continue. And we can see that in line 56, we're actually sending in our scores and our labels, and we're going to choose or get the anomaly threshold to be calculated. And we can see here, for this example, the anomaly threshold has been calculated to be 1.4. And this really makes sense with this image. We can see that 1.4 would be somewhere around here, maybe. Everything 1.4 and above is going to be abnormal. Everything 1.4 and below will be classified as normal. And keeping in line with the perfect example, we often use receiver operator characteristic, ROC curves, in order to gauge the performance of classifiers. And this is the textbook example of what a good ROC curve would look like. Additionally, the area between these blue lines and the dashed lines, the area under the curve, AUC, is equal to 1, and that's also perfect. Unrealistic, but I'd like to show it to you today to show the concept of anomaly detection. Up next, we're going to take our test set of images, pass it through our detector, and actually find out, get a classification of 100, abnormal or normal, of our 33, you can see here that it's a 1 by 33 array of our 33 testing images. It shouldn't surprise you, given what I've shown you already, that all these statistics are equal to 1, that this confusion matrix is perfect. That shouldn't surprise you, given what you've seen. But what I want you to focus on is this function over here, evaluate anomaly detection. And that has given out these metrics that we can see here. And I've worked on several classification problems. I usually, before I knew about this function, ended up calculating these very important statistics from scratch. But it's quite cool to see that there's a function which does it all for you. And you can get specific statistics like this precision, recall, F1 score, and specificity, in addition to things like the mean and global accuracy. As we saw, all 18 anomalous polls were correctly classified as anomaly, our true positives, and all 15 normal polls were correctly classified as normal, our true negatives. And this gives further insight per each anomaly class to see how the network formed. Had there been a slight imperfection in how the model performed, we could actually see, was it the tripped polls that gave the model more trouble, or was it the dirty ones? So what I've shown you so far has been the classification ability of the model. Can it distinguish between normal and abnormal? What we're now going to look at is the explainability. Can it actually give me a good reason or tell me why a given model was normal or abnormal? And these are the heat maps. The first thing we need to do actually is to calculate an anomaly heat map range. And I'll cut to the chase. You'll notice that this variable display range has two values, ranging from 0 to 39. This means that from our calibration dataset, which is supposed to represent the characteristics of our entire dataset, the absolute lowest possible value we got was 0, and the highest possible value we got was 39. This makes sure that the way that we represent the heat maps between normal and abnormal images is consistent. It ensures that we have a standard base to compare all of our results towards. So let's look at an example of an image correctly classified as abnormal. And here's a really nice one. We can see here's a pull without the heat map here on the right-hand side, and it's got a pretty big chip in it. And the heat map quite elegantly shows us why the spill was classified as abnormal. In fact, it lights up and it's quite bright at exactly the spots where the chip has been broken. And this is really cool and really powerful for explainable AI. If we move on down to an example of a normal pull, let's run this section first, and then let's run this one. What we'll notice is that here is an example of a pull where everything's pretty much normal. There are no hotspots in this image. If we run another example, we can see that it looks the same in terms of the fact that there aren't any hotspots. And this speaks to the fact that our data, our image is normal. That brings me to the end of the demo. Before I jump back into the presentation, please feel free to drop any questions or comments in the chat. And as I mentioned, we'll get back to them, or we'll go through them in the Q&A shortly. Let's get back to the presentation. And what we established in the presentation was how I showed you that I taught a machine to see. And if you're interested in more details and the absolute nitty-gritty of that example, please feel free to take a screenshot or scan this QR code over here, and that will take you to the example where you can have a look at it yourself and actually investigate the nuts and bolts behind what's going on in this demo, which I've shown you today. That brings me to the end of the webinar. And what I've discussed today are some of the key fundamentals behind anomaly detection, why it's important, why you'd want to do it, and actually what it is. I did a demo of an FCDD anomaly detector in MATLAB, and what I'd like to encourage you to do is, if you have some data or if you have a use case, I'd love to talk. I'd love to get some more information from you about how we could potentially collaborate. My email address is here on the slide. And once again, here's the QR code for my email. If you scan this, it'll pop an email straight to me and we can chat. Today was the first of 3 webinars in a series that my colleagues and I will be presenting on computer vision. The next one is coming up in about 2 weeks, being Uncovering the Unseen on event detection, and that will be by my colleague Duran Jaffe. And the next one, 2 weeks after that, will be some real-world application of condition monitoring through thermal cameras, presented by my colleague Enzo Duplessis. With that, everyone, that brings me to the end of the webinar today. I really hope that you've learned something new and you've seen the real magic and art and science that is anomaly detection and how it can really be applied in not only a computer vision workflow, but in many other types of data workflows in general. Awesome. I'd like to open the floor for any questions or discussion. Feel free to pop something in the chat or to unmute yourself and discuss anything which you enjoyed. Right, an interesting question here. Hi, Verushen. Do you find MATLAB to be the best software for machine learning? The answer to that is I really enjoy using MATLAB for machine learning because it makes things very easy, or it makes things easier. You know, the example I showed earlier actually had a lot of code written in it, but there are lots of apps in MATLAB that actually let you get started and do classification and regression problems quite well and quickly in MATLAB without you needing to know MATLAB code or how to code in general. So it really lowers the barriers to entry for this type of work. I see a follow-up question, a comment on Python for this type of application. By all means, Python would also be able to give a similar sort of output. You may want to consider also using MATLAB and Python together. You can use each language within one another. And there are certainly advantages and disadvantages to either approach. A really cool thing about MATLAB, however, like in the case study example I mentioned earlier, was that we prototyped the algorithms in MATLAB, and then we could automatically compile that to a DLL or generate C++ code, which could integrate and be deployed with our client systems. So that was a big advantage of using MATLAB in that scenario. It allowed a seamless integration from the data processing stage to the modeling, all the way down to deployment. Thank you for that. Any other comments? Any questions? I note that in the chat, Michelle has dropped in links to register for the upcoming computer vision webinars. I really recommend that you attend them. They're going to be good. All right. Any other comments? Any other questions? Cool. Once again, everybody, I'd really like to thank you all for attending today. It's been great presenting this webinar on something I'm so interested about and so passionate about, and I really hope that you walked away with something valuable. Have a fantastic day further, and thanks for attending.
Thanks. Cheers, guys.